Hey everyone, in this video we're going to talk about MOSFETs. If you're a university student or if you've read textbooks about MOSFETs, you've probably learned about using them in integrated circuit amplifiers, as well as probably understanding their basic molecular characteristics. However, in this video we're going to get into much more practical topics and talk about things employers really want you to know about during job interviews, and general MOSFET topics that will actually be useful for you when you do get a job. Be sure to look at the resources in the Q&A I've also attached to this video in the resources section, as we won't be going through everything I've written in those documents. So first of all, what is a MOSFET? Well, MOSFET stands for Metal Oxide Semiconductor Field Effect Transistor. It's a type of field effect transistor. Here I've shown a model for a typical 3D model of the internals of a MOSFET with its 3 pins, G, D, and S, that stand for gate, drain, and source, respectively. Here is what the packaging for a real-world MOSFET that is through-hole looks like, and here are the circuit symbols for the two types of MOSFETs, the N-type and the P-type, which we'll get into in a second. A MOSFET is by far the most common type of transistor in digital circuits, as billions of them may be included in a memory chip or a microprocessor. This is why I'm going to only focus on MOSFETs in this course instead of other transistors. Now, as a field effect transistor, its primary purpose is to allow you to manipulate the conductivity between its drain and source terminals. And you do this by applying a voltage between the gate and source terminals. This ability to change conductivity with the amount of applied voltage can be used for amplifying or switching electronic signals. When conductivity is negligible, a MOSFET can act as a switch that is off, so current doesn't flow from drain to source. But when conductivity is high, a MOSFET can act as a switch that is on, where current flows readily between the drain and source terminals. There are two types of MOSFETs, as I already talked about, the N-type and the P-type, and they're essentially the opposite of one another and have different characteristics. The main one being that the source type for N-type MOSFETs are electrons, while for P-type MOSFETs they are holes. We won't be getting into this, but if you're more interested, I'll attach some light reading. P-type MOSFETs are generally less efficient. N-type MOSFETs conduct current when a positive voltage is applied between their gate and source terminals. Whereas in a P-type MOSFET, current is conducted when a negative voltage is applied between the gate to source terminals, like so. P-type MOSFETs are essentially inferior in every single way except their ability to switch loads from a high side rather than a low side. So if you had a load, for example, and you wanted to use a MOSFET to switch it, that MOSFET switch, which will show as just a switch, would need to be on the low side of this load resistor. Whereas a P-type MOSFET can be used on the high side, like so. This is critical for devices that can't have their grounds switched, like microcontrollers, because they need to be referenced to the same ground as everything else on their PCBs. Now, a MOSFET differs from many other types of transistors in that it has an insulated gate, the voltage of which determines the conductivity between the drain and source terminals. This is the main advantage of a MOSFET. It requires almost no input current into the gate terminal in order to control the load current that flows through the drain to source terminals, because this gate is insulated. Now, in most applications as an electrical engineer, you will be using a MOSFET as a controllable switch. Sometimes you will be switching this MOSFET on and off very quickly, and sometimes you won't. But It is very rare to use a discrete MOSFET in any other way other than a switching application. The only other way you would use a MOSFET in a non-switching application essentially would be if you were using it inside of an integrated circuit. For non-digital analog circuits like filters and amplifiers, we would typically not use MOSFETs, but we would use operational amplifiers or similar devices, which we will get into in future sections. They look like this. And inside of those devices, they may have tens, if not hundreds of MOSFETs built into them. But those are integrated devices. When we use a MOSFET as a discrete device, meaning we only use a single MOSFET, we're typically going to use it as a switch. So in this video, we're going to focus on that application. So let's get into some of the most common MOSFET interview questions, and we'll just look at the most common one of all. The question is, how do you go about choosing a MOSFET for a given application? Well, here are some of the basic things you would need to know before you can answer this question. Interviewers will probably just ask you this question as an open-ended question and not tell you any details, and they'd be looking for you to ask the appropriate questions in order to be able to answer their question. So it's also seeing whether you can think openly and clearly. The first thing you need to know is, are we using low side switching or are we using high side switching? So would we need an N-type or a P-type? The second question is, how much current do we need to switch? The third would be how much voltage. The fourth would be the logic level of the driver or device that will control the MOSFET. What is that going to be? And 5 is, what are our physical packaging constraints? So for the purposes of this lesson, let's define some basic answers to these questions so that we can properly parameterize our interview question. Let's say we want to use a low side switch to switch on and off a motor. So our circuit is going to look something like this. Now let's say the motor will draw 10 amps of continuous current, and it will switch a 12 volt load as we've shown up here. And we're going to use an Arduino with 0 to 5 volt logic to drive this N-type MOSFET. Furthermore, we are not going to have any packaging constraints except for the fact that we will not have enough space for a heatsink. So the MOSFET must be able to dissipate all of its wasted power within its own package without overheating. All of this is a very typical MOSFET application. So let's get into it first. First off, we need a low side 12 volt across the MOSFET. So what do we need to know? How are we going to go about picking this MOSFET? So here's our circuit. Our first consideration is going to be voltage ratings on the MOSFET. Our first voltage rating is going to be the maximum voltage between the drain and source terminals. Now we're switching 12 volts across this MOSFET, which means that VDS max must be greater than 12 volts. But in general, good engineering rules of thumb specify that we should add about 30% margin to this number. So instead of 12 volts, we'll actually call this 16 volts. That way, we won't break the device too easily. So we're going to rule out any MOSFETs that have a VDS max of less than 16 volts. Next, we want to be able to switch this MOSFET on and off with a 5 volt signal. What that means is that when the voltage at the gate, which is this pin over here, relative to the source is at 5 volts, we want the MOSFET to be fully on. This means that its threshold voltage, or VTH, must be less than 5 volts. The threshold voltage is a parameter for a MOSFET that describes the minimum voltage needed at the gate pin relative to the source pin in order for the MOSFET to start conducting. Again, we want to have a derating of about 30% on this number, so we won't consider any MOSFETs that have a threshold voltage greater than 3.5 volts. So we only want MOSFETs that have a threshold voltage of less than 3.5 volts. Pretty simple here. Next, we also want to make sure that we're not exceeding any gate voltage limitations. So the maximum voltage at our gate to source terminal here must be greater than the Arduino signal that's controlling it. So it must be greater than 5 volts. Again, adding our 30% margin to this number gives us 6.5 volts. So we are not going to consider any MOSFETs for this application that have a VGS max less than 6.5 volts. Next, we want to make sure our MOSFET is rated for the current in which we are syncing through it, which in our case is 10 amps. Adding that same 30% margin, we'll get 13 amps. So we will not consider any device less than 13 amps of drain current. And finally, we have thermal considerations. As the first step, we need to find the MOSFET's RDS on. What is RDS on? RDS on is the effective on resistance. It can be modeled as a series resistor between the drain and source terminals, and it's the effective on resistance when the MOSFET is turned on. It can be modeled as a small resistor. This on resistance needs to be low enough such that there isn't a big voltage drop across the MOSFET. It also has to be low to avoid thermal issues. The MOSFET needs to remain within its junction temperature limits, which typically for MOSFETs are about 175 degrees Celsius. So we need to know the MOSFET's thermal resistance, the junction to ambient thermal resistance, which is typically given inside of a data sheet. So we need the thermal resistance, the junction to ambient thermal resistance. Multiplying this junction to ambient thermal resistance by the power dissipation inside of a MOSFET, which is given by the drain current, IDS squared, multiplied by RDS on. If we multiply all of this by the junction resistance, then we will get a delta temperature over ambient. Adding that to our ambient temperature, we can figure out what the junction temperature of the MOSFET will be and see if it will remain within its temperature limits. Now, since we aren't using this MOSFET in a fast switching application, we don't have to think about capacitive parasitics like the parasitic gate capacitances that are existing on a MOSFET. If we were using it in a switching application, we'd want to know what the input capacitances are, and we would need to calculate the amount of power we would need from the Arduino control pin, which would be proportional to the switching speed. But that aside, we now have our basic criteria, and we want to go and choose our MOSFET. So let's go to DigiKey and try to choose a MOSFET now. Here we are at the DigiKey homepage. Let's go to semiconductors and find discrete semiconductors. Discrete semiconductor product. We then want to go find transistors, field effect transistors, and single field effect transistors. The first thing I do when I get into DigiKey is I sort by in stock, and we'll sort by N channel very quickly. That already eliminates about 33,300 results. Now we're going to apply these changes. Next, we're going to take a look at the drain to source voltage. So we said that we would not accept a MOSFET that has less than 16 volts of VDS max. So we're going to accept everything 16 volts and above. And then we'll go ahead and apply that. Next, we are not going to accept a drive voltage of less than 3.5 volts. And this is going to actually be in the form of our threshold voltage. So we're going to accept anything less than 3.5 volts. We'll do less than or equal to here. And here we go, less than or equal to 3.5 volts. That's eliminated about another 5,300 MOSFETs or so. After that, we are going to limit our VGS max, and we said that we wanted this to be greater than 6.5 volts. So pretty much that's going to be anything up here all the way to plus 40. And then in terms of our current, we wanted to have at least 10 amps of current, more like 13 amps. So we'll start at 13 here and go all the way to the maximum. There we go. We've eliminated another 2,200 results. And then we kind of want a through-hole MOSFET in this specific case, just to reduce the results a bit, and so we can use this on a breadboard or any other device that we want to use it on. It doesn't have to be on a printed circuit board. There we go. We've got everything that we care about so far. Let's take a look if we like this. This is the IRLB8721 PBF. Here's the data sheet, IRLB8721 PBF. At first glance, the VDS max here is 30 volts. That's greater than our 16 volts, so DigiKey did a good job. Next, the gate to source voltage, VDS max, is plus or minus 20 volts. So again, this is greater than the plus or minus 6.5 volts that we wanted. So this is great. The continuous drain current is somewhere between 44 to 62 amps. And so we're pretty happy with this. We're multiple factors below this, so we don't have to worry about this so far. The maximum power dissipation is fairly high. The maximum thermal junction operating temperature is 175, as I previously mentioned. And our thermal resistance is 62 degrees Celsius per watt between the junction to ambient temperature. As we keep going, we'll see that our gate threshold voltage, the maximum gate threshold voltage, is 2.35 volts. This varies because the semiconductor fabrication process is not perfect. So MOSFETs of different types, but in the same manufacturing line, different serial numbers will have different threshold voltages. But this maximum that they've guaranteed us is still better than our maximum, which was 3.5 volts. As we keep going, we see that the RDS on here is around single-digit to double-digit milliohms. And our VGS is going to be closer to 5 volts, and our ID is going to be closer to 10 amps. So this number is a better number here. So we're going to be approximately 16 milliohms of RDS on. So we basically have satisfied every single parameter, except for we have not figured out whether or not this will meet our thermal limitations. So if our RDS on is equal to 16 milliohms, and our drain current is 10 amps, then our delta T, as per the equation I gave before, is going to be equal to 10 amps squared multiplied by 16 milliohms multiplied by the thermal resistance, which is 62 degrees Celsius per watt. And this is going to give us 1.6 watts multiplied by 62 degrees Celsius per watt, which, if we do some quick math, is going to be 1.6 times 62 equal to 99.2 degrees C delta T. Adding this on to our ambient temperature, which is about 25 to 30 Celsius, we'll see will be around 124 to 130 degrees Celsius, which is below the 175 degree junction temperature limit. Therefore, this MOSFET meets all of our requirements. We have successfully chosen a MOSFET. There you have it. You've learned how to choose a N-type MOSFET for a motor switching application to be used as a switch. Now what I want you to do is to take a look at the next item in the course, which is going to be an assignment to pick a transistor for this exact same configuration, except we're not going to use an N-type MOSFET, we're going to use a P-type MOSFET. So I want you to go through the exact same thing we just did, but for a P-type MOSFET, and do it on your own. We'll talk about it together in the next video. Using a P-type MOSFET, we're going to switch on and off this motor from the high side, using again the same 0 to 5 volt on-off logic signal that we have from our Arduino. So go do this assignment, come back, we'll talk in the next video. See you there.